premise of this presentation is that there is no arrow time, only our memory imprints coupled to the direction and velocity we notice whenever there's energy transfer. As usually, this slide allows the reader the option to skip whatever's already known, or at least believed. Again, I do not recommend this bypass since it's a small presentation. If pressed for time or only mildly curious, you may just view the last slide for a summary of the topic. During Newton's time, scientists were debating whether light was a particle or a wave. This debate lasted until Thomas Young demonstrated that light could be made to interfere with itself, meaning light was a wave. But classical waves need a medium. Therefore, he postulated a universe filled with a homogeneous fluid he called the ether, but assumed the fluid to be denser in and around masses. In the 1880s, Michelson and Morley built an interferometer to measure how fast the Earth rotated through this fluid, which was believed to be stationary relative to the Earth. As the Earth rotated, the interferometer should have measured what's called an ether wind, but the interferometer failed to measure this motion. Trying to explain this null result, scientists considered the possibility that space and time were actually one and the same. This became known as space-time. Einstein was fully aware of this belief, and he distilled this belief in space-time into what we call the special theory of relativity. This theory built the concept of space-time along mathematical lines, and to him, special relativity was a mathematical concept without any physical meaning. In 1908, Minkowski formally introduced the idea of space-time as a unified four-dimensional continuum based on a geometric interpretation of the special theory of relativity. At the time, Einstein objected to this interpretation, but this became the foundation for the block universe, where all events, past, present, and future, exist simultaneously in a static four-dimensional structure. In the block universe, the past and the future exist permanently, eternally, while the present is our perception of a thin slice of this universe, and the slide moves forward into this already existing future to become the next now of the block universe. It's like a film where the frames are not sequential but stacked one on top of another, or like a stage where you only see what the spotlight shows and the spotlight is constantly moving. In the block universe, time moves at light speed through the universe. Therefore, if you're standing still in space, you're moving through time at light speed. If you're moving through space, you're still moving through time, but slower. The faster you move through space, the slower you move through time. If you're moving at light speed through space, you stop moving through time altogether. There are many videos on YouTube that show graphs of this interpretation. Although mathematically consistent, this interpretation raises two fundamental questions. Why is time moving, or what is moving time? And why does time move in one direction only? You see, physics equations don't care which way time goes, and even special relativity is silent on both motion and direction. To answer these two questions, I need to modify the accepted interpretation of space-time as dimensions of the universe while staying true to the postulates of special relativity and its results, including time dilation. In other words, the laws of physics are the same in all inertial frames, and the speed of light in a vacuum is constant for all observers, regardless of their motion. As an analogy for space and space-time, let's consider the universe to be a three-dimensional plasma TV screen or a CRT tube with pixels constantly lighting up and going dark all over the screen like an old-fashioned TV tuned to a channel without programming. Each TV pixel is analogous to a space-time pixel being created everywhere in the universe, except that Unlike a TV screen in which pixels light up and go dark, the space portion of space-time remains in the largest universe. This way, space is created and the universe enlarges. As for the time portion of space-time, I first need to develop an analogy in the form of magnetic fields. Magnetic fields are created by and around moving charges. We know this. If an electron or a proton moves, it creates a magnetic field around itself. When the charges stop, the magnetic field falls back on the charges and disappear. Now here's the interesting part. If an observer and a charge are moving with the same velocity in the same direction, there's no magnetic field on the charges. But if an observer moves relative to a stationary charges, a magnetic field is created around the charge. So clearly, a magnetic field exists only when there's relative motion between charge and observer. When there's no relative motion, there's no field. In a way, a charge that's moving relative to one observer but stationary relative to a different observer will have a magnetic field and not have a magnetic field simultaneously. So remember this. If an electron is moving past you, there's a magnetic field. But if you're moving at the same velocity as the electron, there's no magnetic field. Now, let's imagine we could see an electron being created from nothing. We would be looking at nothing and suddenly a point would appear. The expansion of the electron being created from nothing would be identical to an electron moving. Therefore, we will see an instantaneous magnetic field form around a point in space. It would be instantaneous because when the electron reaches its final size, the magnetic field would fall back to zero and disappear. In other words, you will see a magnetic field appear and disappear instantly. I will use this analogy to explain how a time field is created and behaves. In this analogy, the creation of a space pixel is accompanied by a momentary field around it, and that field is not a magnetic field but a time field. That's why I call it a space-time pixel. When the space-time pixel reaches its full size, the time field falls back to nothing, and time at that point disappears. To compare a time field to a magnetic field, both fields appear and disappear instantaneously. So, what are some parameters of this space-time pixel? Well, the time it takes to expand the contract, that's the Planck time, while the size or length of this field is the Planck length. As for its mass, space-time is constantly being created, which means it's not going to have the dimension of kilograms, but of kilograms second. If we do the calculation, that value is 7 times 10 to the minus 51 kilograms seconds, a more realistic value than the Planck mass, which we usually compute at 2 times 10 to the minus 8, a very large number. To me, the Planck units are just the units of a space-time pixel. In this interpretation, time becomes a momentary field the universe creates simultaneously everywhere constantly. But we can't experience this synchronism from everywhere in the universe since light has to reach us with that information. As for the creative force behind time and the time arrow, that's universal expansion. As the universe expands, it creates more space-time pixel, more space, more time fields. The obvious next question is, where does the universe get the energy to create space-time? I answered this in a previous video. So let's explain time dilation now. We believe that time moves at light speed everywhere in the universe. I propose that time evolves, not moves, at a rate comparable to light speed everywhere in the universe. My requirement is that this time creation is driven by a universal expansion that's moving at the speed of light without any acceleration. If you could see space-time being created, as you move faster, time field would appear to be expanding slower, therefore it would take longer for them to reach full size and fall back. The faster you move, the slower time field will appear to expand, and the expansion will take longer. That's time dilation. When you reach light speed, you're moving as fast as time is being created. Therefore, time field creations appears to stop. Time field appear to be frozen. You're now moving and living in the same time field, the same moment. From my frame of reference, time for you has stopped. By a new frame of reference, once you reach light speed, you collide with your destination, whatever that may be. In this interpretation, time is not a scalar. It is a scalar, not a vector quantity. It has magnitude but no direction. Just like mass, volume, density, and other scalar measurement, we can make in a room, we can measure time with a clock anywhere in a room and get the same value. So according to this interpretation, there is no arrow of time, no past to future. Only this moment exists, and it's the same moment everywhere in the universe. One reason we feel like we're moving from the past toward the future is because our memory retains snippets of events and compiles them into the equivalent of a film that we call the past. But in reality, only this moment exists and it's now moving. What we call the past is a collective memory we share with each other, while what we call the future is a personal expectation, what each of us hopes will happen. Those unfortunate to be afflicted with memory disorders lose the concept of a past. To them, neither the past nor the future exist. Physically, we usually visualize how water cooling or the shattering of a falling teacup as an indication of a time arrow, and we'll label it as increasing entropy. The heat from the hot water expands away from the container, and the fragments of the fallen teacup fly away in all directions. But we never see the water spontaneously heating up or the flying fragments recreate the original teacup. Time never seems to go backwards, only forwards. Could this motion away from a collision point reflect something else beside a direction of time? Let's take a careful look at how energy and matter interact with each other. If there were no forces, like friction and colliding objects could deform, energy exchange between colliding objects will lead to instantaneous acceleration. Generally, after collision and the resulting acceleration, objects have different velocities and directions. But what if objects can't really move on their own? What if all motion is dependent on universal expansion? What if the universal expansion is what carries everything at the velocity and direction that objects were given by the energy exchanged during the collision? In this interpretation, universal expansion behaves like a conveyor belt that can carry all objects at different velocity and different direction, but not faster than the speed of light. For example, in a gas, collision between individual gas atoms is random, and universal expansion will carry each atom at a speed and direction determined by the energy exchanged during the collision. Overall, the gas atoms have a random motion, and the degree of disorder is quantified as entropy. But each atom has a definite velocity and direction. Entropy is just a statistical way of looking at many objects and determining probabilities. If we watch every individual atom of the gas, the motion of each atom would appear continuous from point to point, giving us the sense of a time arrow moving in one direction only. But if universal expansion is what's moving those atoms, that motion only has one possible direction, which is away from the collision point. In the case of the cup fragments, that direction is also away from the collision point. In other words, the direction of the time arrow is just the direction of universal expansion, which is three-dimensional. From this perspective, time and time's direction are not intrinsic, but emergent properties of cosmological evolution. The direction of this time arrow is not a built-in feature of time, but a consequence of universal expansion. And the idea that time's arrow might reverse if universal expansion were to stop and reverse, is debatable at best. In summary, time is a momentary field created by universal expansion along space, and we call this creation spacetime. Just like temperature or electric potential, time is a scalar quantity. It has no direction. Our memory stitches moments together, giving us the impression of time flowing from past toward the future. Physically, the impression we have of time moving forward is actually our observation of matter energy interaction, in itself a reflection of universal expansion along three, not four dimensions.